Now we continue study chapter 8, part 2. Section 6, we're going to study two important units. One we call atomic mass unit, and the symbol is U. Another one is the atomic energy unit, we use EV, and also called electron volt, EV. Now, why we study these units? Because when we discuss nuclear energy, of course, there's a lot of energy. But we start with energy from one single proton and neutron. So that's why we use smaller unit. So 1U equals 1.66 times 10 to the power negative 27 kilogram. So almost equals mass of one proton or one neutron. We choose mass of proton neutron as one unit, called 1U. Now for the energy, EV, we call electron volt, equals 1.6 times 10 to the power negative 19 joule. If you remember, that's the unit of energy. And sometimes we also use mega EV. Mega means 1 million. Okay, so 1 mega EV equals 1.6 times 10 to the power negative 13 joule. Okay, so now if you remember, in chapter 3, we studied special relativity, and we studied the rest energy. Mass and energy are related. So now, if I have one U, one proton and one neutron. So now, if we convert 1U of mass to energy, how much is it going to be? So we use Einstein's equation, E sub O, that's rest energy equals mass times speed of light and a square. And this is mass. Okay, this equals 1U. Speed of light and a square. So if you do the calculation using calculator, you're going to find answer give you roughly 1.5 times 10 to the power negative 19 joule. So now if we use the unit we just studied, give you 931 mega EV. That's quite a bit of energy from 1U, from one proton or one neutron. So now we're going to study a very, very important concept called binding energy. Binding energy, very important. Binding energy is the nuclear energy, nuclear fission, nuclear fusion. Okay. So first we want to discuss why the nuclear can stay together. Look at these two figures I downloaded from internet. Okay, this is uranium. Uranium 238. That means you have 238 proton plus neutron. And uranium 235. This is the one we use for fission. Okay, 235. The proton and the neutron, or nucleons. So why we call them uranium? Because they both has the same number of protons, 92, but a different number of neutrons. Okay, so now, we want to discuss why so many proton neutrons can stay together. In first place, well, the protons that have a positive charge, they're going to repel each other, right? So how you can have so many stay together? Remember, this is very, very small inside of an atom, like a blueberry in the football stadium. Remember? Okay, so how they can stay together? So electric force going to repel each other. 92 positive charge. The reason because there is another force we haven't studied yet. So we're going to study today. It's called strong nuclear force. very strong, 100 times stronger than electric force. But this force is very different from other forces because this force has very short range, means only inside nuclear about this size, so they can hold each other only if they're close enough. Okay, so this is very interesting. So now we're going to discuss a little detail about this force. Remember, this is called strong nuclear force. And energy hold them together, we're going to call binding energy. Okay, so since 1930, so scientists studied the nucleus very carefully. They find this. They find a hydrogen and a neutron. When they are separate, the mass is this much, 2.0165 U. Now, if the hydrogen atom and the neutron combine, then what do we have? We have an isotope we call deuterium. So now the deuterium we suppose have same mass like a hydrogen plus neutron, right? But it's not. So the mass of deuterium is smaller, 2.0141 U. See, they're different. Look at this figure. Okay, so when hydrogen and one neutron separate, they are heavier. But when they combine together, okay, become lighter. So what's the difference? That we do a single mass, we call delta M. The difference between two masses. Subtract these two numbers, give you 0.0024 U. Now, if we can convert this mass to energy, use the rest energy equation, mass, speed of light, and square. Okay, so now this little bit mass is going to give you 2.2 mega eV of energy. Okay, so what this experiment tell us? This tell us a very important conclusion. When proton and neutron combine and form nucleus, certain mass is missing, this much mass. In other words, certain energy is given off. We use that equation and find the energy. Okay, so read again. When proton and neutron combine and form a nucleus, certain mass is missing, and certain energy is given off. This energy we give a name we call binding energy. Okay, look at this figure again. So when the proton neutron separate, they are heavier, greater mass. But when they combine together, what happens? When proton neutron combine together, give you a nucleus which is lighter than they're separated. Then at the same time, certain energy is given off. This energy is the nuclear energy, we call binding energy. When proton neutron combine, become lighter and release energy. So now, okay, this give us binding energy. We use BE. So energy given off when proton neutron combine to form nucleus. All is energy equivalent of the missing mass. Mass times speed of light square. All the energy needed to break up a nucleus. So now if you have this nucleus you want to break up, become separate, you need this much energy in before you break up. Okay. So binding energy is very high. So one pair of proton neutron give you 2.2 mega eV. Uh, so if we calculate, we can find this conclusion. Every kilogram of mass, 1 kilogram, can give you up to 800 billion kilojoule energy. That's a lot of energy. For example, if a 1 kilogram uranium can give you 800 billion kilojoule of binding energy. And this energy is enough for 500,000 families use for 1 month. Assume you use 400 kilowatt hour per family. So that's about the population of Arkansas, right? We have about roughly 2 million people, and every 4 people per family, so it's going to be about 500,000. Okay, so it seems like we found a new way to use to make energy. So if I have many proton neutrons, we combine them and it will give you a lot of energy. But we cannot find many free proton neutrons because they are combined. Okay, we can find all kind of elements, like in this periodic table. You can find hydrogen, helium, the nitrogen, oxygen. You can find gold, mercury, or Uranus. But you cannot find many proton neutrons. So scientists have to think a different way to use nuclear energy. Okay, so now section 8, we're going to discuss binding energy per nucleon. First, what that means? That means the total energy divided by number of nucleons. Okay, so we know when proton neutron combine make a nuclear, the energy cannot be same for every element, right? For example, like helium, we only have 2 protons, 2 neutrons, 4 nucleons. Mercury, well, 200 nucleons, of course. So when proton neutron combine make helium or mercury or Uranus, going to be different energy. So now we want to find the average energy. That is the total energy divided by the number of the nucleons. So for helium, going to divide by 4. Mercury divided by 200. So we found the bonding energy per nucleons. That's very important. Okay, so now around 1830, scientists studied the periodic table very carefully, find the mass of every element. So the mass of the hydrogen, helium all over the table. Okay, then they calculate so how much energy, the binding energy, then bonding energy per nucleons. Okay, so then they find something very important. They find this. For the isotope of hydrogen, the bonding energy per nucleon is 1.1 mega eV per nucleon. For helium, it's 6.8 mega eV per nucleon. But for iron, the metals, it's 8.6. And for uranium, is the 7.4 mega eV. So which one give you more energy? Not the very light one, not the very heavy one, the medium-sized one give you more energy. Okay, so here's what they find. So the horizontal axis is the number of nucleons. So they studied from hydrogen all the way to uranium. They find which one give you more energy per nucleon. Uh, so the conclusion is not very light one, not very heavy one. The medium-sized one give you more energy. So medium-sized one. So now scientists find a conclusion. If we can use uh, the proton-neutron make a medium-sized nuclear, okay, will give you more energy, more bonding energy. So how we can make a medium size? There are two different ways. One we call fusion. So if we can use a lighter nuclei, combine them, give a medium size, well, you should have more energy out. Or we call fission. So if you can break down heavy nuclears, make two medium size, then what happens? More energy out. So either for fusion or for fission, as long as you can make a medium-sized one, there'll be more energy produced. So let's read again. This is very important conclusion. We're likely going to ask you in test. The medium-sized nucleus is more stable, and it is given off more binding energy. So the strong nuclear force is a very short range force, and the medium size give you more energy. Medium size give you more energy. So that's the fission and the fusion. The fission is to break heavy nuclear into two medium-sized one, more bonding energy out. The fusion is to join or combine two lighter nuclei to form a medium-sized one. So then what happens? More bonding energy out. Okay, next section we're going to study nuclear fission. We're going to discuss a little detail. So we just studied nuclear fission is break a large or heavy nuclear into smaller one, make a medium size. Okay, so now the first one, first elements scientists choose was uranium. And we understand why, because uranium is heaviest one you can find. Uranium is about here. Okay, so now uranium. So scientists choose uranium-235, which works better than 238. Uranium is unstable, but the half-life is very, very long, like 1,000 years, right? A million years. So we cannot wait that long. So what we're going to do, we're going to force fission. So scientists use a neutron beam. So one single neutron strike uranium-235. Why use neutron? Because neutron has no charge. So smaller force between. So proton not work as well because proton has positive charge. It's hard for proton joining the nuclear. It's easier for neutron. So anyway, when one neutron join uranium 235, okay, then become 236, right? Because one neutron added to 235. Now this one become very unstable. Going to be break up to two pieces. So again, one neutron join 235, become 236, then break down right away. So when uranium-236 break down, there are many different possibilities. One of them is these two, strontium and xenon. Okay, so one heavy nuclear break up to medium size. Then what happens? You see the red color one. This is the binding energy come out. Okay, so now at the same time, not only binding energy, also two neutrons come out. Because if we add 140 plus 94 give you 234. But you have a 236 start with, right? So two neutrons will come out. That's very important because these two neutrons are going to go other uranium-235, then do the same thing. So we call the chain reaction. Look at this diagram. So one neutron break uranium-235, 236, then give it two medium size, give it energy, and plus two more neutrons. These two neutrons will go other two target, 235, then become 236, then break up. Okay, give you more binding energy and two more neutrons. And another one also give you two more. So it's double up. One give you two, then four, then eight. Next week, one going to be 16, 32, 64, 128. So double up, double up. That's called the chain reaction. At least one neutron produced per fission. Then induce another fission. In our examples, there's two neutron per fission. At least one. At least one. Okay. So now the nuclear fission, of course, can produce a lot of energy. And we have two applications. One called nuclear reactors. So fission at controlled rate. So like a nuclear power plant, we have two nuclear reactor in Roswell, Arkansas. Okay, produce nuclear energy. Another application we call atomic bomb. Really, we should call nuclear bomb. So that fission at uncontrolled rate. So chain reaction speed up, double up, give a lot of energy, then explode. So that's two applications. Okay, we're going to discuss a little about how the nuclear reactor works. So this chamber, inside we have two rods. One, see the brown color one called fuel rods. That's the uranium or other fission materials. And then we have a control rod. The reason because you don't want the chain reaction go too fast, right? So this rod will go up and down, control the rate of nuclear reaction. So this photo from our textbook, you can see that's the chamber, the chamber. Okay, so now see this one is another a diagram. So there's a chamber. Okay, then we have uranium rod. This 1, 2, 3. And these two control rod go up and down, up and down. If it's necessary, it slows down the nuclear reaction. Okay, so now we do not use nuclear energy directly. So produce a lot of energy. Then first of all, we have the cooling water. The cooling water. Cooling water become steam because nuclear energy. Transfer energy to the heat. Okay, then you go to a steam engine. Then produce mechanical energy. Then you go to a electric generator. Electric generator produce electricity. So from nuclear to heat, mechanical, then electricity. Okay. Now we're going to discuss a little about nuclear fusion. By the way, we still cannot use fusion energy because it's too expensive. Okay, the fusion is by definition is joining two light nuclei to make a medium-sized one. Here's one example. We have two isotopes of hydrogen. these two combined will give you helium plus one neutron, so you can continue the chain reaction. Then plus 17.6 factor eV of bonding energy. So deuterium, the tritium, two isotopes, give you helium, give you neutron plus bonding energy. Okay, so now we have many advantages of the fusion energy because very efficient. You see that's more energy output and very safe, no pollutions, and also we have unlimited supply. We can find this isotope from seawater, for example. But we have problem too, because the fusion need some very important conditions, because the the nuclei, they do not like join each other, right? Because they are both have positive charge. So how we can make the positive charge join each other, make fusions? Well, first of all, you need a very high temperature. So if the temperature high enough, then they have very high speed, so have a chance to join each other. But then the temperature turn to be very, very high. That's 100 million degree. So it's very hard to make this kind of high temperature. And second, you need very high concentration. You need enough particles. Then they have to join each other long enough, so produce fusion energy. Here's the chamber. You can see that's one person stand there. You can see how big is the chamber. So scientists still do research, use a lot of electricity, the magnet, lasers, do everything to join the isotope together, make fusion energy. So far scientists can make fusion happens, but too expensive. So we cannot use fusion energy for industry or commercial purpose. Okay, this is the end of chapter 8. Thank you very much.